Thank you, Tim. Wow, there's so a lot of people. Thank you all for joining us today. Today we have Dr. Frederik, who is a visiting faculty researcher at Google. And I've been reading a lot of paper from Frederik, who is obviously a leader in pushing hydrological forecast with machine learning and deep learning. So today he will be talking about long short-term memory networks, LSTM, for rainfall runoff modeling. Um, yeah, the floor is yours, Frederik. Take it away.
Thanks. Thanks for the introduction. Thanks for having me. Thanks for everybody who joined. Yeah, let's see. So the talk today is going to be mainly about my research work of the last years and not so much about Google's flood forecasting initiative. So just as a disclaimer at the start, but I'm happy to answer questions to this as well. And with that, let's see. Before I start with my main presentation, I want to start with like a small recap, a small introduction to the problem itself, because I know there are some hydrologists in the room or some environmental engineers, but probably not everybody is following what I've done in the last years or knows the problem, so that we can are all on board and can speak about the same. I will quickly introduce what's the problem that we are trying to solve. So imagine you're looking at the map and you point to some random river. And now you want to know how much water there is in this river today or tomorrow or in like 5 days. Or you want to know how this river might evolve in the future. This is task in hydrology is called rainfall runoff modeling. And that's the task I've been working on over the last years. And rainfall runoff modeling is important for several reasons for society. Some of the more obvious ones are probably flood forecasting or drought monitoring and modeling, but there's also water resource management for the agricultural sector of hydropower. And I already mentioned it slightly, but it's also important for estimating the future behavior of rivers, because we know the world is changing and we are constantly trying to build constructions and flood protections. And for that, we want to know how a river might evolve looking 10 years into the future, giving some climate change scenarios. So for the rest of my talk, there will be a few concepts that are important to understand. And probably the first and most important concept is what is a basin or a catchment for everybody who's not from hydrology. So what we see on this map is a digital elevation map of parts of Austria where I'm currently living. Higher elevations mean lighter color mean higher elevations, and darker color mean lower elevations. And so if we, for example, look at this river at the point, at this red point, and we want to know about the stream flow of this river, the stream flow at this point is influenced by a certain area. And this area, which we can see, I think, here now, yeah, in yellow, this is called the basin or the catchment. And for simplicity, let's say it's only defined by the catchment, by the slope of the terrain, meaning any point of precipitation that falls on the surface follows the steepest gradient. So every drop of precipitation falling in this yellow area will eventually reach this red dot river point. Some of it might evaporate, be lost, but if it will influence one river, it will be this river. And now there's another concept that will be important for the rest of my talk, which is what is lumped modeling. So in hydrology, we refer to lumped modeling when we model an entire area by spatially averaged signals. So what we do is we take this area, we compute the spatially averaged precipitation, the spatially averaged temperature, and we use these spatially averaged inputs It's like time series inputs into a model to then model and forecast the stream flow direct dot. And this is only works for like certain settings, but this is the most common setting in hydrology. Now you can imagine that depending on where you are in the world and depending on the environment and the climate and whatever, natural rivers behave completely different. So for example, in the lower left, you see an arid basin in Arizona that falls completely dry during most of the time and only sees spikes in discharge signal at like individual days throughout years. While, for example, in the upper left, we see a typical hydrograph from a snow-dominated catchment that has very low flows during the winter and freezing season, and during the melting season in summer, we see elevated discharge, with eventually flood peaks. All of these environments have different hydrological processes that are important or the main drivers. And if we want to model all of these rivers, the model that we train and use needs to be able to capture all of these processes. And in the last decade, hydrologists developed a plethora of physics-inspired or conceptual hydrology models. The most common models are so-called bucket-type models. And in these models, there are different states that are really conceptualized as a bucket for snow or soil moisture or groundwater. And the transition functions between the inputs and in between the storages are predefined and contain a handful of model parameters. And these models are usually forced by just precipitation temperature. And then the entire system is modeled to predict discharge. And yeah, so there are a handful of parameters that still need to be calibrated for these models to work. And I might make myself unpopular at the very beginning here, but just to be provocative, I would say that there was very little development, very little advances over the past decades with these types of models. And still today, in the research and also operationally, the models that are used were actually developed in the 70s or 80s. So what's the state of these hydrological models? How good are they? So this is a slide with data from when I started my PhD. These kinds of plots, we will see them a lot, so I will spend a bit of time to explain what we are seeing. This is a cumulative density plot of the NSE distribution. In this case, this is the NSE of 400 different catchments from the Chemins data sets for two different models calibrated in two different settings. So the models are the VIC model, which is quite popular in the States, and the LHM model, which is quite popular in Europe. And both of these models were trained on the same data, the same periods. And once they were trained per basin individually, like for every basin, the model parameters were fitted to match best the observations in this basin, which is represented by the dashed line. And the solid line denotes a regional calibration scheme. That means we train the model with some parameter transfer functions to all basins at the same time. So if we look at this plot and we would draw a horizontal line at 0.5, and then we look at the cross-section with these CDF lines, what we see on the x-axis is the median performance of these models. And we can see very clearly that for both models, the per basin calibrated models are much better than the regional calibrated counterpart, even though it's the same model. And this trend is true across all hydrology models, these traditional hydrology models. But we are at the machine learning, deep learning workshop here. So for everybody who knows about the trends for machine learning, getting worse with more data is actually quite in contrast to the trends that we see in machine learning, where our model gets significantly better the more data we have. And this is specifically true for the subfield called deep learning. So the question that I asked myself, like at the end of my master and then at the beginning of my PhD, is how can we make efficient use of data in hydrology with the ultimate goal of building better models? And the question is, can we use deep learning models in hydrology and then see the same trends that if we train like regional models, we get better than single basin models? And we will now come to the main part of my talk. So before we go over some results, I want again go one step back. And as the title already said, my talk is mainly about the LSTM, or the so-called long short-term memory network. And with this slide, I want to convince you why there are very good reasons that this particular model is a very good fit for the problem that we are trying to model. And the reason is that LSTMs are conceptually similar to any hydrology model, or to how we as a hydrologist imagine the world, the hydrological environment, but with some advantages. So if we look at the left, we see one typical hydrological bucket model. And the hydrology model, as I said previously, has some system states like soil moisture and snow, and these states represent the real-world processes. And if we want to formally describe the system, we can say that the system states at time step t are a function of the current inputs at this time step, the previous model states, and some model parameters. And now the discharge, the output of this model, y hat, is a function of the updated system states and some more model parameters. And now if we look at the right, which depicts a scheme of the LSTM cell, this is actually how formally we can also describe the LSTM. The LSTM also has internal system states. In fact, it has two. But these system states are similarly to hydrology models or the hydrological world, updated at every timestamp as a function of the current inputs, the previous states, and some learnable network weights. And the output is a function of the updated states and some additional weights. The big difference between the two modeling approaches, however, is that the LSTM can learn anything that is useful to solve the problem and that is deducible from the data, while hydrological models can only model what is predefined in the model routine. So there can be two problems. We either miss to include very important processes. For example, interception in forests is most of the time not implemented in hydrology models, but reduces the effective precipitation by a lot. And the other thing is, even the implemented processes might be implemented wrong because the equations that we use could simply just not be like the reality. So to reference the question from just 2 slides ago, can deep learning help rainfall-runoff models to become better with more data? The short answer is yes, and I will present more details in the upcoming slides. But what you see here is that a single regional LSTM, which is the solid line again, is much better than the per basin hyperparameter tuned and trained LSTMs. So again, both models were trained on the same data, the same periods. Just one model was trained to predict. One model was trained on the combined data of all rivers in a data set, while the other model, the solid line, the other models were trained to each river individually. And if you remember the plots from the hydrology models, this is exactly the opposite of what we have seen there, where the regional counterpart is way worse than the per basin calibrated model. So if we compare this to hydrology models, here we can see it directly. The left plot only shows models that were calibrated in a regional fashion. It's the two models that we have seen before, and the yellow line is the LSTM. And even if we compare on the right-hand side the regional LSTM to per basin calibrated hydrology models, all of these dashed lines, we can see that the LSTM is still better than the best practice for hydrology models. And all of these benchmark models were trained by experts of these models or the model developers themselves on the same data, the same period. And yeah, so this is nothing new, actually. This was published in 2019. Surprisingly, we will see that, yeah, we come back to this later. The question is maybe for you, why is regional modeling so interesting? Why am I personally so interested in getting very good regional models, and I'm not satisfied with having single basin calibrated model? And there are actually two motivations. The first motivation, which is linked to my work at Google, is that most rivers of the world are actually ungauged, meaning they have no historic measurements that we can use to train a model specifically for this river. And this is specifically true for low-income or developing countries, where some of the most severe floods are happening. And we have seen how poor hydrology models regionalize. So I personally want to find a way how we can do better. And second motivation is that what is called prediction ungauged basins, or how good is a model to predict in a river that it was not trained for, is also some kind of a holy grail in hydrology. And the International Association of Hydrological Sciences actually dedicated an entire decade to solve or advance this problem. But to quote from a summary paper that was released at the end of this decade, there's still a long way to go in terms of achieving robust and reliable predictions, and most progress during this decade was actually made in engaged rather than an ungauged basin. So to conclude, an entire decade has actually yielded very little gains in terms of getting better in predicting in ungauged basins. So the question is, how well does the LSTM generalize to unseen basins? So far, everything that I've shown you was just evaluation on time splits, meaning that we train on certain years and then we evaluate on different years, but using all basins in the training data set. So how good are we if we exclude basins from the training data sets and then only use them to evaluate? Because an often heard critique is that deep learning models only overfit to training basins and they're just fitting numbers and don't understand the system. But clearly, if they are able to predict in basins that they have never seen before, then they learn something that represents what's actually happening. So in a different paper, we looked at this, and the results are here. This is also from a very old paper now. Yeah, so the new model, which was trained on a k-fold cross-validation setting, is the yellow line with the asterisk markers. And the other lines here is, again, the reference model from before, the gauged model, which is the yellow solid line. And then there are two hydrological benchmark models. One is the former US, or now it's actually the former US national water model, the Sacramento Soil Moisture Counting Model, which is a per basin calibrated model. So this is not run in pub, but instead is calibrated for each basin individually. And the other one is the now former US national water model, but still the operational one, which is the solid blue line. And this is calibrated for thousands of stations across the US. So this is not really retrainable on our data set. It's more like but it's evaluated on the same stations at this point. And we can see that the LSTM in ungauged, on average, is better than the hydrology model being trained in the best practices. So being trained per basin, and the LSTM not being trained on this basin, the LSTM is still better in the majority of the basins. And here's another benchmarking from a recent model intercomparison study led by Juliane May. This benchmarking study was, I think, so far the most strict and robust test of model intercomparisons that I'm aware of in hydrology. So Juliane and her colleagues invited different groups to participate, and everybody got access to the training basins and only the training data. And then we had to submit model simulations for the validation periods, but we were only able to submit simulation once. And once everybody submitted, Juliane and her team computed all the metrics and everything. And these are basically the results. So this plot is a bit different, but essentially what we see is 4 plots, and the rows are basins in these P color plots, and the rows are the different models, and the columns are basins. And we see on the left-hand side the different models that participated, and on the right-hand side of all of these 4 boxes, we see the median KGE. And now the upper left box is calibration locations, so training basins during, if you look at the very right-hand upper side, during the calibration period. So this is training basin during training period. No surprise that deep learning models usually are very good during training periods, and this has absolutely nothing to say about the model performance at all. Then the more interesting thing is if we, for example, go directly below, we see the training basins, but during the validation period. And we see again that the LSTM is like the much better model, better than the second group of models, which is denoted by these 2 black solid lines, which are per basin calibrated hydrology models, and much better than all of the regional hydrology models that participated, which is the lower block of models. And if we now look at the lower right, we see validation locations in validation periods. So this is PAP basins that were not part of the training data, and a period that is different from the training period in the training basins. And we see the huge drop that most or all of the models have, but we also in performance terms, but we see that the LSTM actually degrades the least of all of these hydrology models, and still has a considerable high mean KGE, even though it's PAP now in a completely different period. If you're interested in more on these, go check out this paper. It's, I think, a really interesting study. Okay, so next, I want us to spend a very few, like a minute or so to watch one video, and then we'll discuss why and how these models are actually achieving their performance. So what we are seeing here is a lab model of 2 catchments. The 2 catchments are the 2 blue boxes. And both of these catchments have the same size, the same slope, and get the same meteorological forcing. So they have the same temperature, get the same precipitation. However, you can already see that both of these blue boxes respond completely different to their meteorological forcings. So the left box is already like producing a lot of runoff from the upper tube, and it's very dark and muddy water, while the right-hand box is now starting to drip water from the lower tube, which is very clear, and it's very slowly. So the left-hand box already completely stopped draining any water, while the right-hand side box only started. So if we want to have a single model that is able to predict the discharge in both of these boxes, what's the additional input we need here, apart from just the meteorological forcings? And I bet you figured it out yourself. In case not, these are certainly the catchment attributes. So there is information additional to just precipitation and temperature that is important to be able to describe what's happening here. And this is, for example, the land use here, the vegetation that is needed for the model to understand the differences. So, sorry. Okay, so how does it work? This slide is probably the only thing that I want you to remember from today's talk. And again, this is nothing new. It was already published like years ago, but trust me if I tell you that this is the #1 mistake I see being done in all hydrology publications with LSTM still today. So if you use LSTMs in hydrology, the first thing is you never want to train an LSTM on data from just one basin, but you always want to train on multiple basins. And even if you're just interested in one basin, you still want to train the model on data from more basins, because you will still get improved performance in your basin of interest. And the other point is, and that's the link to the video, you want to train the LSTM on a combination of meteorological time series features and static catchment attributes. And this is really important, because only if you provide additional static catchment attributes or some form of features that allow the model to differentiate between catchments, only then it is able to learn a transferable understanding of the hydrological processes. And now let's go back to the difference between single basin models and regional models. And what I'm going to show you now is something that I've never shown anyone before. The next few slides are from an upcoming paper, and yeah, you're in fact the first people to see these results. So in a recent paper, what we did, it's a paper led by Jonathan Frame, we looked at how well do LSTMs perform on events, on peak flows that are outside of the training period. So what we did per basin, we computed the return periods of the data, and then we split the training and the test data in the following way. Every year where the maximum annual discharge is above the HQ5, a 5-year flood, we put these years in the test year bin, and every year where it's below the HQ5, we use this data as the training years. So here training years are the orange line, the orange segments, and the test data is the green segments, and the horizontal dashed lines is the HQ5 computed for this basin. So far, the only thing that I said regarding single basin models and regional models is that single basin models are just like worse in terms of performance, but there's actually a reason why they are worse, and I think this reason is much more interesting than just being worse in an NSE or whatever. And the reason is that single basin models will never be able, but single basin models, LSTMs, if you train them on one basin, are not able to predict a discharge value that is higher than the maximum discharge value it was able to predict during the training period. So what you're seeing here now is the same basin from the last slide, but now the observations are in blue, and we have the simulation during the training period. So the fitted data in orange, and the simulation during the test period in green. And the horizontal line now is denoting the highest, like the absolute highest discharge the model predicted during the training period. And it's like the year 93 or something. And what you are seeing that this is like a natural threshold for this model. The model is not able to predict anything above this. And I mean, this is actually no novelty. Like one of the critiques I heard the most at the beginning of my research was that machine learning models are not able to extrapolate. We can never use these models to predict events that were unseen at the training data. And that's certainly true, but only if you train single basin models. If you train regional models, this is what you see. The model is actually able to predict values larger than the highest prediction during the training period. Then in the test period. And the reason is that the model has seen larger discharge events in different basins. There are different basins that have higher discharge values, and the model is therefore trained to see larger values, trained to output larger values, and it's able to transfer this understanding from one basin to the other basin. And if we look at this in a more formal way, this is an adapted plot from the Jonathan Frame paper, but now comparing the regional LSTM versus the single basin LSTM in terms of absolute peak bias. So that the percentage error that we do on the peak flow, just looking at the annual maximum flow, and now binned in return periods. And on the very left, you see the training performance, so they're smaller than HQ5, and everything else is test data. And you can see that also the regional LSTM gets worse with higher events. But the single basin LSTM actually gets worse faster, or gets worse more severe, if you want so. And in Jonathan's paper, he compared this to hydrology models, and I can tell you here that for hydrology models, it's even more severe, so they are even worse. And this is now only looking at KG and LSE or the peak bias, but I also looked at all other kinds of metrics that we commonly use, and the regional model is better in any metric than single basin LSTMs if you look like on average over like a large sample data set. And so this is like one of my last slides, and that's the current state of publications in hydrology. I think you have certainly seen that the number of publications, including LSTMs, is increasing by a lot over the years. And we did some literature research over a subset of papers being published in 2021. And actually, almost 80% of all publications still trained LSTMs as single basin models, even though like the regional model papers were like 2 years old, or almost 3 years at this point. And over 50% of these 80% did a study including only a single basin, and the remaining almost 50, so it's almost a one-to-one split, trained single basin LSTMs, but at least included more than one basin in their study. Also interesting is that out of these 80% that trained LSTMs for each basin individually, 30% cited the regional model papers that clearly said you should never again train single basin LSTMs. So they cite them, but still train single basin models. And from the remaining 20% that trained regional LSTMs, there's around 20% of the publications were with direct involvement from me or one of my colleagues from the last papers. The remaining 20, there's another 20% from Chao Peng's group of Penn State, and then the rest is from various people. And I hope that I talk today, and also whatever will be published in the next years, that these statistics will change, and over time people will understand that if they use LSTMs, they have to rethink how you should train a hydrology model, because it's just a different kind of model, and we should not apply a deep learning model in exactly the same way how we applied hydrology models over the past decades. So at this point, I reached the end of my presentation. There's, I think, just one conclusion that I want you to get from today's talk, which is like never ever train a single basin LSTM. And yeah, with that, I'm open questions. Thanks.
That was wonderful. Yeah, thank you so much. I loved your final send-off image with the sad Spider-Man. Wonderful. So we have roughly 20 minutes left in this hour. So if there are any questions, feel free to just raise your hand. Biplav and I will help manage the inflow of information and questions. Let me go to the chat real quick and see if there's anybody who has any pressing questions up at the very beginning. And Biplav, why don't you kick it off and I'll check the chat.
Yeah, thanks, Frederik. Great presentation. I have a question on the static watershed characteristics that you incorporate in LSTM models. Because when you think about it, it's in the back propagation process, it's doing the differentiation, right? So when you incorporate these static characteristics, doesn't it essentially become zero? Or like, how do you incorporate these static watershed characteristics in the model?
I'm not sure if I fully understand your question, but these are inputs to the model. These are not parameters of the model. So you don't backpropagate on the inputs, you just backpropagate on the weights of the neural network. And this is just another input, like you input precipitation. So actually what really is happening, like the most simple way, and so far the best way, is to just concatenate the static inputs to your dynamic inputs at every time step. So instead of just passing precipitation and temperature as the inputs into the LSTM, you pass precipitation, temperature, elevation, land use, whatever. And you don't backpropagate to these inputs.
Okay, yeah, that makes sense. Yeah, I have one more question on the hydrological processes. With the traditional hydrological model, you have a clear equations or whatever on infiltration, evaporation, all those things, right? But with LSTM, you probably have to look into the cell state. So is there a easier way, because it sometimes gets very hard to interpret or get those values from the cell states. So could you maybe share your experience on like how would you go about interpreting those values, and how do you link those probably to a physical processes that's happening on the hydrology?
Sure. Yeah, I have I've done some research on model interpretability, and I actually looked quite a lot at cell states, because I mean, these are the states of the model over time, and we expect that something like snow or soil moisture is captured in the cell state. But instead of looking at individual cell states, which I've also done in the past, which I would not recommend anyone to do anymore. I think we even have a slide on this. Let me check. Yeah. So I co-authored a paper led by Tommy Lees, where what we did was we extracted the time series of cell states from the LSTM. So for everybody not familiar with the LSTM, the cell state is really just a vector. And if you say hidden site, 128 for the LSTM, what it means is that your cell state has 128 elements. So the model has the capacity to store 128 elements over time. So what we did was to extract the time series of these cell states from input time sequences. And now, instead of looking at individual cell states, we said, well, the LSTM can distribute information in any way across cell state. There's nobody forces the LSTM to say snow has to be stored in an individual cell state. There could be the perfect information about snow stored in this vector, but distributed across 5 cell states. Could be cell state 1 plus cell state 3 minus 1/3 of cell state 5 or something like this. So what we did was we took in this paper, the ChemistGB data set, we trained the regular model from just attributes and forcings to discharge. And now we wanted to see how much information on soil moisture or snow is stored in the cell state. Mm-hmm. And what we did was, given the cell state time series, we fitted a linear regression, one linear regression. So I think the LSTM only had 64 states in this model, so 64 weights plus a bias for all basins combined. So it was one linear regression for all of the basins. to regress from the sail state to soil moisture or from sail state to snow. So this linear regression is not able to do anything specific to one basin. If there's something like soil moisture in it that is like globally representative of all basins, then this linear regression will be able to find it. And yeah, and the result where we looked at soil moisture at different levels, the performance varies across the soil moisture depth here or groundwater. But in general, you can extract soil moisture, and that's also true for snow. I don't have the plot here, with just a linear regression from the sail states. The only problem is you need some soil moisture or some snow information to be able to train this linear regression. But we actually tested it, and you can use I think it was something like, I don't know, a year of data per basin or even less, because really you're just fitting 64 weights. It's not like there's no magic happening. So you need very little data to then be able to output soil moisture or snow from a model that was only trained on discharge. You can certainly also, if you have data to train a model, more data, you can also just train the model to directly output soil moisture and snow during the training process. You can just have the model output 3 values, discharge, soil moisture, and snow. But yeah, most of the time I would say we don't have that much snow and soil moisture data, so you probably want to focus your model. And it's also, we don't have observed data, and probably from my experience, I would say you fit your model on the observation that you have, which is discharge, and it learns the important processes along the way that you are then able to extract from the model post hoc. Yeah, sorry for the very long answer.
That was wonderful. Yeah, thank you so much. So we do have 3 questions and a raised hand. So let's go out to Tien Du. Sorry if I mispronounced your name, but the floor is yours. I think you were the first to put in a question.
Oh, yes. Thank you so much for the presentation. I really enjoyed it. Yes, I always wonder if LSTM can predict the extreme events. So through your presentation now, I can understand that it actually possible. And also I realized the video that you show also seeing the difference between the catchment attributes and then how the runoff come out from that. So I have the question, do you actually use your catchment attributes in your LSTM models, both in the basin and also regional models? And another one is that, how do you actually transfer the result from catchment regional? I mean, when you do the catchment regional, each result gonna be still applicable to that local only, right? So does it mean actually the other basin can also transfer the result to the other basin? Yeah, I'm not sure if
I'm not sure if I understand the second part of the question.
Yeah, yeah, I just don't know how this means, what is the difference between the LSTM. I understand about when you have a big large scale model, then you can actually calibrate the individual basin and also multiple basin. But for the LSTM regionals, when you calibrate, it's still gonna be applied to that location only, right? But then how can the other location can transfer the result to that location? Yeah.
Okay, so maybe the first question, if we use static catchment attributes, seems like it was not clear from our presentation, but yes, this yes, we do, as much as possible, and they are just concatenated at every time step to the time series input, like the meteorological inputs. And this is really important. If you train in regional LSTM, you should use meteorological time series and static catchment attributes. And yes, this is what we do. And the other question, if I understood correctly, the question was, the model that I train in a regional fashion, how can I use this model for different basins? Was this the question? like basins that were not trained, part of the trained data set?
Yes, like how, because I think in hydrological model, even though you have like the large scale models, when you calibrate them, the result is gonna be still like applicable to that location only, even though we use like multiple basins.
Okay.
And then,
I'm not fully sure I understand the question. I try to answer it. So the model is still trained in a way that the input, like if I do inference, one input sample is just for one basin. So I provide a time series of inputs from one basin. And this is like, again, the dynamic features and the catchment attributes. And it will predict the discharge for this basin. It's not that I provide the forcings and attributes from all basins at once, and it predicts, let's say, 500 values, and these are the discharge of 500 different points. The model still is used in a way that I can infer for each basin separately and how I can then use this model to predict the different rivers. It's just, instead of using the inputs and attributes from one basin, I use inputs and attributes from a different basin, and then use the same weights, the same LSTM, and I get discharge for what the model thinks is the discharge giving these inputs. I hope this answers your question.
yeah.
Okay.
Thank you so much.
Amazing.
Yeah, sorry
Thanks.
for making a very complicated question.
Oh, no problem. No problem.
No, that's great. And the whole point of this session is capacity building, right? So it's good questions. So we have another question with only 9 minutes left, and I think we've got 3 on the line. So Banu Magtra, the floor is over to you if you've got a question.
Yeah, I can also try to repeat the question and answer the question so that we don't have to wait. Like, if you, I don't know if Banu is.
I was still on that.
Okay, the question was if what we have seen from the LSTM enabled to predict discharge, if I think this will also be true for different processes like soil moisture, ET, and the physical model, like training in a multi-basin fashion. I know it's at least true for groundwater. I know it is partially true for evapotranspiration. The problem there is a bit that we don't have that many large sample data sets, because that's the key point, right? We need large sample data sets. We want to have data sets with ET measurements from a lot of places. And yeah, so my short answer is I think it should generally be true for physical processes in the environment. That's like, I think, what I would say, state processes in the environment. ET, you can argue if it's instantaneous or not. Yeah, okay, next question, maybe.
Yeah, so I think that's mine. Just a really good, and first, great presentation, Dr. Kratzer. I really enjoyed it. But I wanted to ask about PUB. So whenever you're predicting in ungauged basins, do you think restricting the training set to similar catchments could be beneficial? Or do you think that's always adding as much data as possible should be the way to go?
Yeah, I cannot 100% answer this question. We did some experiments in this direction where we, I don't know if you've heard of the Caravan dataset, which is like a combination of different chemist datasets, but with unified forcings and attributes. And what we did was we trained an LSTM. I know we left out the fraction of ChemTS basins and then only trained on the remaining ChemTS basins, or we included all basins from around the world, so it's Great Britain, Brazil, Chile, Australia, and we measured the performance on the same holdout set of basins in the US. And so far, it seemed like it's always better to include as much data as possible. I would not say this with 100% confidence, so maybe a great paper idea for you to, to test. But I think, yes, I think the more the better.
I got you. Thank you so much.
I think I'm next. Hi, thank you so much for your presentation. That was great. I was wondering, so you showed a slide that compared a single basin model versus the regional model, and we saw how much the peak flows predictions were improved with the regional model. But I know that that's just an ongoing challenge with rainfall runoff models in the first place, is getting those really peak flows. And that, of course, has huge implications when those peak flows are underpredicted for the flood modeling world. So I was just wondering, what do you think is the path forward for improving those peak flow predictions with an LSTM model? Do you think that it's just a matter of having more data, or do you see another path forward?
Yeah, great question. And very relevant to our work. Okay, so first of all, I want to say the saturation problem that I showed you, there's a small caveat though, which is the regional LSTM still has this saturation problem, but only at the basins with the absolute highest discharge in the training data set. So if you look at the data with the absolute highest discharge, you will still see that this is like now the far end of the discharge distribution that the model is able to predict. And this is one point where we can certainly try to improve, and which is actually something that I'm discussing in my team every day at the moment, which is finding ways on how to completely resolve the saturation problem from LSTM-based modeling. And in one way, this could mean maybe experimenting with data augmentation and artificially using this like much higher discharge data, and we have to see how we can augment the inputs so that it matches for the model. Mm-hmm. So this is one path forward. I think looking at data augmentation. The other thing is, I think certainly more data also helps more, because I think a lot of the peaks that the model is not able to get are due to the fact that we use very coarse, globally available meteorological data sets. But some of the most severe peaks are convective small-scale events that are maybe not as represented in the input data. So using more precipitation inputs, higher resolution or more regional, higher resolution data sets in the inputs as well could hopefully also help. And getting more discharge data certainly will also help. Like it sounds stupid, but the amount of training data that we have openly available is still not a lot. Like most of the data comes from the US, and like the countries that are interesting from the flood perspective, there's very little data actually to be able to include them in your training data. And I mean, I showed that we are good in PUB, but you're certainly much better if you have training data. So yeah, I think this would be my 3 points. It's more discharge data, more and different meteorological inputs, and trying to solve the saturation problem that is still present in the regional model, but not as severe.
Thank you so much. That's a great answer.
Well, we only have 1 minute left, and we have a bevy of questions.
Yeah, I can stay 10 minutes longer.
That's wonderful. Yeah, thank you so much. Let's go over to Miguel. Miguel, are you there?
Can you hear me?
Yep, I can hear you.
Okay, sorry, like something wrong happened with my microphone. So just continue the compliment for this great presentation. I was just wondering about this LSTM data model. How do you represent the uncertainty on this model? Are you able to create an ensemble, for example, for like for operational purposes, kind?
Excellent question. I hope I have a question for this as well, because it's actually much more interesting what you can. I think I don't have a question. So what you can actually do with these models is, instead of just regressing and predicting the discharge value, you can predict a probability distribution. So what we're actually doing, and there's a paper published on this by my friend and colleague Daniel Klotz, instead of predicting just discharge value, you predict the parameters of a mixture of distributions. And in this, here we are using the asymmetric Laplacian, a mixture of asymmetric Laplacians. And so what the model is really outputting are the parameters of a probability distribution, and then you really get an uncertainty distribution at every time step of your predictions. And now you can get whatever percentile value that you want directly from the distribution. This is what we actually at Google use operationally as our model output. And if you have, and the other thing is, if you have information about uncertainty in the inputs, then my best bet so far would be to try to include as many inputs as possible. Because, for example, ECNWF, the precipitation, they have actually 50 different ensemble members. You can use just the control member, or you can also try to use all 50 precipitation ensemble members and let the model learn in which parts of the world which ensemble member is the most representative. Yeah, so I did mention this today, but actually this is a very interesting probability. That's not only true for LSTMs, but for any kind of neural network-based model. You can directly train and learn, let the model learn to predict probability distributions. Yeah, and thanks, Asha, for putting the name in the chat. There's also, I have this here somewhere. Sorry, it gets a bit confusing. There's this non-Google research blog listed here. This includes all publications that me and my colleagues have done on this topic. So you can find all of these papers that I mentioned today on this blog. And sorry, one more thing, we still use an ensemble. So yes, we use probabilistic outputs, and we use an ensemble of 3 models here at Google. So we do both.
Excellent, thank you so much. So if I'm able to do one small question regarding that, when you are doing the probabilistic, actually in classical hydrology, when you are representing this uncertainty, you are kind of differentiated between the one that the simulation that follows the physics, like the behavioral and non-behavioral models. Are you able to identify just some simulations that are outside of this law of physics?
Another very good question. I've actually an intern in our team is currently working on this topic. So I can't tell you too much because it's still ongoing work. I have to say, so far we haven't seen many examples where the LSTM, if it's trained regional and in the fashion I presented today, did something that is physically unreasonable. But yeah, they are still, for example, the saturation would be something like this, right? That's there should be more water in the system. So yeah, in short, I can't tell you at this point, but there should be some updates in the future.
Excellent, thank you so much.
Wonderful. I think Priyanka is still on the line with her hand up. Over to you.
Hi, Dr. Frederik. Thank you so much for the great presentation. My question is actually goes with the uncertainty that you are answering. My question is when you were training the model with the data taken from other calibrated model, have you looked at the uncertainty associated with the calibrated model results?
I am not quite sure on what you've. We never trained an LSTM with input data taken from a different calibrated model, only if you mean the weather model. Like the only input to our model is precipitation, temperature, and so on from like a global weather model and static catchment attributes. We don't use any hydrology model as input to our model.
Okay, got it.
Okay.
Thank you.
Wonderful. And then I see Guta's back in the call. Over to you, Guta.
Yeah. Can you hear me?
Yes.
Yeah. Thank you, Frederik. So my question is that traditionally, like hydrological models, in addition to producing, for example, the main output variable we are calibrating, for example, stream flow, we also get evapotranspiration or soil moisture or variables like that. And sometimes for our studies, those variables are actually more important than whatever we are obtaining at the outlet or the stream flow. So with the LSTM, I mean, we can obtain a really good performance with the stream flow, for example, at the outlet. But what is the current progress on like being able to obtain other outputs from the model, from the LSTM itself, or coupling the LSTM with the traditional hydrologic model itself?
Yeah, I don't know if you missed my answer to the question regarding the state analysis, but you actually can get information about soil and snow from an LSTM that is only trained on discharge, and it's described in the paper linked here at the bottom. Sorry, I'll probably not repeat the entire process here. There is also work done by, for example, Xiaoping Shen's group at Penn State on training hybrid models that go a step back and hard code system states into the model, but let the model still be trained by backpropagation. This can be another way. I want to say, though, that this is a very personal opinion, that the additional outputs that you get from hydrology models, like soil moisture and snow, I mean, you get them and they are defined like by definition as being soil moisture and snow, which doesn't mean that they have anything to do with soil moisture and snow in the catchment in reality. And there are certainly a number of studies that show that the soil moisture that you have or the snow that you have in the model state has little to nothing to do with reality. So I got this question a lot over the last years, and I have to say it's a bit annoying to always be asked to get something from LSTMs that hydrology models provide, while the hydrology model provides information which is completely useless, if I want to be very provocative here. So again, the answer is you can get the data from hydrology model, from LSTMs as well. It takes a little bit more of effort, but then you actually get data that representing soil moisture and snow in your catchment. And I wouldn't count too much on what you get from the hydrology models.
Okay, thank you.
All right, so I'm skating through the chat right now. I feel like most folks got their questions in, and I know a couple people dropped off who did have questions. Any other final questions on the line?
Yeah, otherwise also feel free to reach out by email or Twitter or whatever, and try to answer your questions.
Well, perfect. I just want to